Let's do another example. We'll look at this function x squared plus xy plus y squared, and I'd like to know where the max and min points are on the disk. And when I say the disk, I don't mean just the circle, I mean the interior too. So really, we could think of this as a less than or equal sign to think about what's happening inside the disk in the interior. We'll think about critical points. I won't do that right here, but you can check, you should check, there's a critical point at 0, 0, right in the middle of the disk. But to ask out what's happening on the boundary, we'll use the method of Lagrange multipliers. So to do that, we need to know the gradient of the function f. We need to know the gradient of the function g that defines our constraint. And if these are to be parallel, which we want, then we can solve this system of three equations, the first two given by the components of the vectors, and the third given by the constraint curve. There are three variables here, x, y, and lambda. As I mentioned before, we don't care much about the value of lambda, but knowing it sometimes can help us find x and y. So I'll do something a little different than we did in the last. Maybe you can recognize that it would be pretty easy to solve both the first and second equation for lambda. That is, I can divide on the left by 2x in the first equation. That's equal to lambda. I can divide on the right, on the left of the second equation by 2y. And that's also equal to lambda. And some red flags should be going up saying, wait a second, you've got x and y in the denominator. That's trouble because x could be 0 or y could be 0. And you're absolutely right. But if you look at that first equation, if x were 0, then it follows that y would also have to be 0. And likewise, the second equation says the same thing. If y were 0, then x would have to be 0. And actually, we don't have to worry about that because the point 0, 0 is not on the circle x squared plus y squared equals 4. So there are no points that might be a solution where x or y is 0. So we're just okay dividing by x and y here. So why is this a helpful thing to do? Like I mentioned, we don't really care about the value of lambda, but if the thing on the left is equal to lambda and the thing on the right is equal to lambda, then those are equal to each other. And that gives us an equation relating x and y. We can cancel the 2's in the denominator. We can cross multiply and get some other terms that cancel out. We conclude that x squared has to be y squared, but we know since this is a point on the constraint that x squared plus y squared is 4. We can replace y squared with x squared. And we conclude that x has to be plus or minus 2. I'm sorry, plus or minus square root of 2. Well, and if x squared is y squared, then y also has to be plus or minus the square root of 2, and these can happen independently of each other. Knowing one for x doesn't mean we know one for y. So this gives rise to 4 Lagrange critical points, and we'll check the values of each of them. And then we'll also add our critical point 0, 0 to the list as one to check. Let's head over to Sage, and we'll let the computer do all the computations for us. So here in Sage, I've defined the function x squared plus xy plus y squared. I've drawn a picture of the contour plot together with a circle that is the constraint curve. We can see in the middle there's that critical point 0, 0. Actually, in this picture, we get the idea that that is a local minimum. And then at plus or minus root 2 for x and y, sort of the 4 corners, we see geometrically what we expect. That is, the contours for f, the black contours, are parallel and tangent to the red contour, the contour for the circle. So let's let Sage do all the work and compute these 5 values for us. And we see that the z-value is 6. So in the northeast and the southwest. You can see that here on the contour plot. That the z-value is 2 in the northwest and the southeast, and that our critical point in the middle, there's a value of 0. And if you want to see what the 3D plot looks like, actually let's put the constraint curve in here. Here's our 3D plot. So this elliptic paraboloid with our circle, unit circle in the middle. And yeah, we see 2 maxes. There's these 2 valleys that aren't quite minimums. They are along the boundary, but the critical point is the global minimum on that disk. So when we see that these are the values at all 5 of our points for Lagrange critical points and 1 honest critical point in the middle of the circle, and 1 of those points is a max. I'm sorry, 2 of those points are global maximums. I didn't circle that second one. And then the one in the middle of the circle is a global minimum.